Good morning and welcome to this recording. It's going to be covering basically chapter 38. So in this chapter there are actually some key ideas that basically was at the start of a new branch of mechanics, things that we couldn't explain basically using classical mechanics. So one of this phenomenon is basically what this whole chapter is the fact that unlike what Mr. Actually Maxwell has done and the experiments of Mr. Young and the stuff that we saw in optics, that light basically is a wave. So this is going to basically argue otherwise. Light is a particle. Okay, I mean, in a sense, it still keeps, of course, its wave nature. So, for example, if we do the experiment with the Young experiment, namely either the double slit experiment or the single slit, where we have light that comes through a single slit, for example, and produces those patterns of diffraction. So you have a beam in here of a given frequency lambda. So when it comes in here, and if I have a plate in here, I'm going to see the intensity, a very bright middle spot in here, and then followed by, this is the stuff that is usually done in physics too. So in here we have a dark fringe or dark spot. Okay, dark fringe actually is going to be small one, and then followed by another bright, and so on and so forth. And this is, of course, is symmetrical. The intensity, if you guys remember, is peaked around the middle, and then it's going to start slowly become less and less as you move away. But it's not zero anyway. And this minima and this maxima are given by the laws of basically, especially the minima in here, that's what we know about it, is in the case of light is given by the expression of m lambda equals to, if I believe, what is it? I'm sorry, is it m lambda or is it, this is the stuff that we saw in optics. Yeah, it's equal to a sine of theta, where theta is actually depending on where I am looking for that place where all the waves cancel using Huygens principle, and the a actually is a measure of the opening in here for the single slit. So this is a proof that light, if you wish, is a wave, because the only way that we can explain this one is basically doing wavelets and interpret that. However, we're looking at least on several phenomenon where light actually does not really behave as a wave, but it behaves more as a particle. One of these experiments actually that was done toward the turn of last century, and that is the experiment involving light. So for example, if I have a cathode in here where I am connecting it to a battery, and that battery, for example, has it doesn't matter what the voltage right now is, so I'm not going to throw in numbers, but this is a battery in here. Usually in this experiment there is a control resistance in here, or actually more of a rheostat than a resistance, where a variable basically a resistor, so depending on where you pick it. And then there is, of course, an anode in here. So there is a current, there is a galvanometer in here that you would want usually to read the voltage in here, I mean the current in here that is flowing through this circuit, to see how many electrons are actually moving around, if there is any. Okay, so here is the experiment. You shine light in here, okay, on this metal, and you turn on the voltage. Okay, if you turn on the voltage, or actually what you will notice is that there is a current in here, and that current is actually going to be established only and only if the frequency in here is bigger than a certain threshold. Okay, so it doesn't depend on the intensity. In a sense, if you double the intensity or triple the intensity for low frequencies, this is not going to be seen. So there is a frequency in here that it seems like light has to have in order for it to be absorbed by the material in here, and then the electrons are freed, and they're attracted to the anode in here, and they complete the circuit, and you will see the current flowing through this one. Okay, so what you do in this case, you reverse the polarity of the battery. So you make this one as a positive, this one is a positive, and you make this one as a negative, and you see when can you stop this electrons, because remember the electrons are flowing this way. Let me come up with a different color. So you have an electron that is flowing in this direction, okay, toward the anode, But then, if you reverse the polarity, that this is negative now and this is positive, if you have high enough voltage in here, you can stop them in their tracks. And actually, how we can tell, by making sure that the current that is you're going to have in here is going to be 0. So basically, in a nutshell, this is how the experiment look like. And there is a voltage in here where this one actually happens, where you're going to, and that is the stopping voltage or stoppage voltage, where you're going to stop the current from flowing. So actually, this is how the data basically can be summarized in a nutshell. So what I'm looking in here, I'm looking at the intensity of the current as a function of voltage. So this is the applied voltage across this end. So this is what I mean by VAC. Okay. If VAC is positive in here, and I have a certain frequency, what I notice in here is that more or less, so this is the voltage is equal to 0. Actually, you don't need actually voltage to begin with. So if you the current is going to be steady, depending, of course, on the voltage. So the more and more you increase the voltage, the other voltage, the one that was positive, not this one. So all you're going to increase is the current initially, but then it reaches saturation. You cannot reach it if you reverse the polarity, as I was talking about in here. So there is a point where this current will drop to 0, and that current is the so-called stoppage voltage. Okay, so this is for a given intensity of the light. Now, granted that this frequency has to be higher than a certain minimum, below which you cannot do this. There is no current. You're not going to see any current, no matter how much voltage you apply there. Okay? Because, and then we'll see the explanation for why that is. Now, if, for example, you change the intensity, okay? So that means in this case, the current, that's all, it's the same frequency. The current, for example, if you double it, you're going to see a double intensity. So again, it's going to grow and then reach the saturation in this case, but the current will be doubled with a higher intensity, a brighter light, if you wish. And this experiment has to be monochromatic, otherwise we'll have a problem, of course. So you have monochromatic. In other words, the frequency has to be unique in here, otherwise we have a problem, because you will have all kinds of frequencies in there. And again, the stoppage voltage for the same material is the same thing in this case, so it doesn't change. Okay, so that is something that is that's how the experiment is. So basically, if you double the intensity of the light, the current doubles. So what you're looking in here is a current. So this is a so-called photoelectric effect, and this is what is used on most of photoelectric effect, and this is what is used most of on the houses nowadays to generate electricity. Okay, so let's try to explain that. And Mr. Einstein actually relied on the work of Mr. Planck that was actually published about 5 years earlier to explain this. This is how actually Mr. Einstein became famous. It's not because of his work of relativity or anything like that, for that he won the Nobel Prize. It's because of this work actually in the photoelectric effect. So basically, this is how he explained it, that based on Mr. Planck's work on the black body radiation, which again we're going to see in the next chapter, what he basically postulated is light is actually made up of tiny particles, and those tiny particles he called them photons. Okay, these particles, of course, must have energy and they must have momentum because they are particles. Again, even light has, a wave has an energy, but the distinction in here that this ones must have momentum, and that is something that we need to find basically, because a wave does not really have a momentum in a sense like, for example, it says something that doesn't work. So what he's saying in here is that, look, if you have the right frequency, those are tiny particles. They collide with the electrons and they knock them off of their basically the attachment to the atoms, and then they will leave. Okay, so that's basically the interpretation for that, how it happens. And for the threshold, basically, he assumed in this case that there is some sort of a minimum work function, he called it, basically the energy level at which these frequencies must exceed in order for them to be extracted from their basically material. Okay, so having empowered with that, this is basically the interpretation that he came up with. First of all, the energy. We know that a photon, at least at rest, doesn't have mass, so if we apply Newtonian relativity for its energy, E for the, in general, of course, if you guys remember, E is equal to PC squared plus MC squared. That is the energy in relativistic terms, but because it's a photon at rest, has no energy, has no mass, so therefore its energy in this case must be PC. So that is one relationship that I'm going to use in here. Furthermore, he postulated, as I said, that the energy per Planck's work, this is where he referred to Planck's work, okay, on the black body radiation, is proportional to the frequency, and he used the same symbol, which is H, and that is Planck's constant, which is 6.626, I guess, times 10 to the negative 34. And in SI, so this is the unit for it, it's just joule over second, okay? I'm sorry, joule times second, because the frequency has units of 1 over second. So it is an action, actually. So this is the units for the Planck's constants. Where is my pen? Okay. Okay, so now we have that, and then we want to use this expression now to find the momentum, because from here clearly the momentum for this photon must be E over C, and remember E is equal, I just argued by Planck's constant, work, it's hf divided by c, and if we use the dispersion law that basically says that the speed of light is just the product of the wavelength times the frequency, from here we're going to come up with the relationship, if you wish, between the momentum and the wavelength in general. So the momentum in this case is going to be equal to, actually we don't really need this expression until later. Okay, but hold it, okay? So probably we'll need that expression right now just to express things in terms of how the wavelength is related. So again, I'm going to use the ratio of F over C as just from this expression basically. F over C is just equal to 1 over lambda, and this is how the momentum is related to the wavelength, and this is actually the momentum of these particles now, the photons, okay? We will need this expression later on to for the Compton scattering. Anyway, so for light, actually, for a current to be established, the electrons must at least reach this point in here with some velocity, and that is going to be the drift velocity in the circuit, and therefore their kinetic energy must be greater than at least this frequency minus, basically that's the whole argument that he made in here. So in general, the kinetic energy in this case must be equal at least to their energy that they emerged with from the collision, in this case, with the particle of light, which is hf, minus of course the work function, because if that does not happen, you cannot have any kinetic energy. The electrons will not escape. So you really need to have a minimum frequency, and that minimum frequency is equal to the work function divided by. This is a property of the material, of course, property of the metals. Okay, so in a sense, you need a certain minimum frequency for the electrons to actually emerge with any velocity whatsoever, in order for you to kick them out of there. Again, this is not quantum mechanics yet, so we're still using classical mechanics to explain things. So, and that is the kinetic energy with which they will escape, 1/2 of the mass of the electrons times their velocity squared, and from here they reach the anode, and basically they complete the circuit. So the frequency in here has to, in order to have the kinetic energy greater than 0, of course it's always positive if you want to expect any value whatsoever, the frequency must be greater than a certain cutoff, below which there is no that. So that's his explanation basically of the photoelectric effect. Okay. Actually, we can actually take it a step further for the stoppage voltage in here, because the stoppage voltage also was measured, and we can clearly see that the stoppage voltage is actually dependent also on the frequency in this case, and this is how it depends on the frequency. So if I reverse the polarity so that the electrons do not come back, so basically do not emerge. So if I reverse the polarity as I was talking about in here, I expect the current to stop. So that means the electrons will have no kinetic energy, and for that I use a conservation of energy. In this case, kinetic energy is equal to potential energy. For a single electron, the potential energy is just charge times the voltage. So this quantity in here must be equal to the charge of the electron times the voltage, and this is the stoppage voltage. This must be equal to the kinetic energy of that electron, which is given by HF minus phi. And from here, we can clearly see that the stoppage voltage is proportional to the frequency, of course, too. Okay? So in other words, the higher the frequency, the higher the stoppage voltage. And that's exactly what the photoelectric effect experiments have yielded. So this is, again, one thing that clearly indicates that light is made up of particles, as Mr. Einstein called them photons. Okay, so this is an experiment that clearly indicated that light is made up of particles made up of photons. Okay, they have specific wavelength, they have specific, but they have specific momentum, and of course an energy that is equal to their this expression in here. Okay. We take this step further. Mr. Compton in 1922 conducted an experiment with X-ray, which is super high energy particles. Super high energy, not X-rays, gamma rays actually. Okay, or actually even X-rays too. Because you will see that the wavelength is in that range actually of the X-ray. Okay, so high energy photons. Okay, so this is the Compton scattering in this case. So in other words, if you're wondering will it work with the regular light, no. Okay, you will see why clearly. Okay, so let's see how that is. So what he did was basically he has a target in this case. Okay, and he has in this case an incoming light of a given frequency, in this case, and wavelength lambda. Okay, well, in this case what he noted is that the light is scattered in this case. Okay, and it emerges with a different wavelength lambda prime. This is not like the one that I was talking about. This is not the diffusion like I was talking about to begin with. This is not like this experiment, because the wavelength in here is the same. In this case actually the wavelength is changed. Okay, so that's one thing. As a matter of fact, he computed the change in the wavelength, and he found it equal to a quantity lambda equals to lambda e, and that number actually was due to him, and we're going to find this value times cosine of pi. Okay, where phi is this angle. Okay, so if you move around at some points, this number actually is equal to 0, namely when there is no change basically in the wavelength in this case, and there is if you move around all the way around. So that's basically how he collects the looking just at how the wavelength is changing. Now this lambda e is a fixed number for the electron. Lambda e is equal to 2.4, I think, 26, 10 to the negative 12 meters, okay, or 2.426 nanometers, okay. I'm sorry, picometers, okay, picometers. This is a very, very high energy because it's very, very short wavelength in this case. As a matter of fact, if you're interested in finding what's the frequency of this one, which you just see over the wavelength, it's going to be of the order of 10 to the power 20. Okay, it's going to be 10 to the power 20 hertz. So this is a very, very high frequency. Okay, so we're not talking about stuff of low frequency in here. That's why you cannot really you cannot see it actually with longer wavelength in this case, because lambda e is very, very tiny compared to the difference between the two wavelengths, so it's going to be the same thing, okay, for regular light. Okay, so Mr. Compton knew immediately that that's probably due to the particle nature of this photons. Okay, so the color changes actually. I know that we're in the X-ray region, so we cannot see them, but the frequency itself is changing. Okay, so how can we explain that? Again, we're going to use relativity in this case to explain these things. For a photon, for an electron, so what we have in this case, we have an electron sitting minding its own business, basically, practically at rest, and in here it's hit by a wavelength, okay, by a particle of a given wavelength and momentum p. Okay, so this is the incoming particle. So we're going to treat this one as a regular collision. Okay, incoming particle, and the electron in here has no velocity initially. Its momentum p naught, if you wish, is equal to 0. Okay, after the collision, actually what happened in this case, we have the emerging photon will have a different wavelength and a different momentum associated with it. The one that we're interested in a specific angle phi. Okay, and the electron now is no longer at rest. It could have a momentum. So this is basically what this electron will end up with. It's going to end up with its own momentum after the collision. So this is typical collision. In other words, if you're really interested in the mechanics of this, so basically what you say in this case, the incoming momentum as a vector p is equal to the outgoing momenta, which is in this case p prime plus p of the electron. Okay, so that is basically conservation of momentum. Conservation of energy in this case dictate the following. Before collision, we had, of course, the energy of the electron, which is in this case is going to be just Pc. Okay, the energy of the photon, which is just its momentum times the speed of light, plus the electron, although has no kinetic energy, if you wish, has no component coming from motion, it still has the fact that it has its rest mass. So we're going to add that to it, and here in this case it's the mass of the electron times the speed of light squared. Okay, so why did I square this quantity? Okay, no, I didn't mean to. I needed to square it later on. Okay, so this is basically the quantity in here for. So this is the energy before. The energy after, again, is going to be p prime times c plus, I'm going to write it as the total energy of the electron. Okay, the total energy of the electron, if you guys remember from the chapter 37, is in such a way for a particle is equal to, for a particle that has a momentum and mass in this case, so it's momentum times c squared plus the rest mass in this case for the electron, which I'm going to just leave it as m. I'm not going to address it with an e squared. Okay, so that is basically the total energy. So I'm going to take this expression in here. This is the energy, conservation of energy in this collision, whereas the first one is just conservation of moment. So those are the two conditions for the collision in this case. So I'm going to take this expression in here and rearrange the terms, move this one to the other side, and square everything, because I know what the square of that quantity is, which is this one. So I'm going to take Pc minus, it's a good idea to put it next to it, friend, P prime c plus the mass of the electron times the speed of light, this is the energy before, is equal to the energy of the electron. If I square both terms, this will be just give me the other side in here, which is Pe c squared. Remember, this is a vector, okay? So I mean, we're going to get this quantity quickly, okay? So plus the mass of the electron, c squared, the whole thing squared. Now I square this quantity: square of the first plus the square of the second plus the square of the third plus the double, the cross terms, okay, which they're all going to be doubled. So it's going to be p squared, c squared plus p prime squared, c squared plus, there is no such a term in here, plus mc squared squared plus now the cross product, cross terms, okay. First of all, 2p p prime c squared, or is that minus? I'm sorry, that's a minus, plus 2pm c cubed minus 2p prime m c cubed, okay. I need to find this term in here. First of all, you can clearly see that there is a cancellation in this equation. This term and this term are the same. I'm going to get rid of them right away. I need to get from the conservation of momentum, I'm going to get the p for the electron being just the difference of the momenta of the two photons. So the p of the electron is going to be the initial p minus the outgoing p for the photons from this expression, okay. Now square this quantity because we need it in here, and we're going to find pe squared is equal to p squared plus p prime squared minus 2p p prime. But that's actually a dot product between these two vectors. And the dot product between these two vectors, if you can clearly see from the geometry in here, what is the geometry of the photon? So here is p, initial p, I took it in this direction. Here is p prime, and this is equal to the dot product of p times p prime, these vectors. The angle between them is cosine phi. So from here it's clearly is going to be the magnitude of first, magnitude of second, and times cosine. Okay, so we're going to develop that. Because I need to multiply this by c squared in the expression, so I'm going to c square this expression. So it's going to be pe squared c squared is equal to p squared c squared plus p prime squared c squared minus 2p p prime cosine of the angle between them, which is exactly phi. Okay, now let's look at this term in here, because this equation in here coming from the conservation of energy. Actually, there is already clearly, you can see that this term and that term will cancel, this term and that term will cancel, and then I have a bunch of 2's that are left, okay, that they will cancel. Let's write that expression first. I'm going to write the left hand side first. I have p squared c squared plus p prime squared c squared, those are the first two terms in here, minus 2p p prime minus 2p p prime c squared, okay, that's the third term in here, plus 2pm cubed plus 2pm c cubed minus 2p prime m c cubed. So that takes care of this term. Now is equal to the second half, which is just pe c the whole thing squared, which is this whole expression in here that I was writing in there. Okay, so it's going to be p squared c squared plus p prime squared c squared minus 2p p prime cosine of phi. As I was telling you, I mean, as we was going through this, we're talking about it. This term and this term and this two terms also cancel mutually. Furthermore, the terms that are left have all of them 2 in it, which I'm going to cancel right away. So I'm left with this expression that look like, and another cancellation if you guys probably have seen it too. Let me write it, do it in blue now. So this term, the c squared that is left, oh no, sorry, there is a c squared in here that I forgot, because I multiplied, remember, by c squared everywhere from this step to this step. See, this is the mistakes that you see, because I multiplied, in order to get from here to here, I multiplied by c squared, and I forgot to do it for the last term. I just was concerned about the dot product, and I forgot the c squared. So there is a c squared term in here too. Okay, so there is c squared in every single one at least. So there is this c squared that cancels, and then from the c squared I'm left with 1, and from this c squared I'm left with 1. So after all of these cancellations, this is what we're left with. From here we'll be left with minus pp prime. Okay, so let's leave that minus pp prime. From this term we're going to be adding pmc. Okay, from the other term we're subtracting p prime mc, and from the whole side on the other side we're left with just minus p prime cosine of phi. If we move this to the other term, it's going to change its sign, and we are in business. So what we have in this case is we have pmc minus p prime mc is equal to, did I get the signs correct? I think so. Okay, is equal to 1 minus cosine of phi times p prime, pp prime. Okay, we're going to do one last step in here, and that is to divide actually by pp prime. Divide by this term, or multiply by the inverse of it. Obviously the p and the p cancel, and I will be left with mc over p prime, minus the p prime and the p cancel, and I will be left with an mc over p. And this expression, the p and the p prime cancel, so I will be left with just 1 minus cosine of phi. We're going to use the expression how p and p prime are related to lambda prime using this expression that we derived earlier when we were going from. So we know that p is equal to h over lambda. Okay, so p is equal to h over lambda, and in the same token I'm going to say that p prime is equal to h over lambda prime. This is the outgoing photon, and this is the incoming photon. Having that, we'll place it in this expression. The lambda will go upstairs and the lambda prime will go upstairs, and we will have an h in the denominator, and it's the same factor that is going to be common for both of them. So let's do that. mc over h times lambda prime minus mc over h times lambda is equal to 1 minus cosine of phi. Normally we write this expression as lambda prime minus lambda is equal to h over mc times 1 minus cosine of phi. Okay, so this is the expression that Mr. Compton basically was able to explain with his experiment, the fact that this number lambda e is actually for the electron turned out to be exactly what we said up there if you replace the value. So lambda e is equal to h over the mass of the electron times the speed of light. This number is 6.626 10 to the negative 34. This number is 9.1 times 10 to the negative 31 kilogram, and the speed of light is 3 times 10 to the power 8. If we plug in all of these numbers, this number, as I was saying, is 2.426 10 to the negative 12 meters, and it's a length. Okay, so that's basically in a nutshell what this whole thing is arguing. Then this actually, light is indeed made up of particles. Okay, so this experiment, if it did anything, it confirmed the hypothesis of Mr. Einstein. So light is made up of particles. I know the experiments with Young and all of that, and actually we're coming to this one to derive an important result in here. Let me go back into that optics basically experiment that we mentioned in the beginning. So we have in here an opening. I'm going to call it A, again for a photon that is coming in here, and I'm going to come in here and look at the light, and again the light is maximum, and then it's going to reach a certain minima, and then actually it's going to go and get another peak, and so on and so forth, and it's going to have a second minima up there and another one in the bottom, and it's symmetrical. So basically this is how the light is scattered through a single slit. So this is the single slit experiment. Okay, and if I am interested in this dark fringes, where they happen, they're governed by this expression. M lambda is equal to basically a sine of theta. Normally, we do this distance very far away, and we're controlling this parameter so that this theta is very small. Theta is roughly equal to its tangent of theta, and it's roughly equal to sine of theta. And this, of course, theta is in radians. I was in an experiment with some of my students in the past, and they were finding errors big time because they were using degrees instead of radians for their for this approximation. This is basically because sine theta is just what, theta minus theta cubed over 3 factorial. For small theta, theta cubed is negligible, and cosine theta is just 1 minus theta squared over 2 factorial, and that is also for the same thing. If I neglect anything of the order of theta squared or higher, this approximation works. So in other words, the first dark fringe, which tell me how big this spread is, how much we're spreading this one, is going to happen for m equals to 1, of course, in that expression, and that is going to happen at lambda equals to a theta of 1, okay? And we did this experiment and we find theta 1, okay? So in this approximation, of course, where theta is very small. Okay, so let's see now with light what's going on. So here is the problem. I send a beam of light. So in here, I know the light is coming parallel, for example, to the x-axis. So I know its momentum must be in the x direction. But for some reason, instead of having them, if they're really particles, okay, if they're really particles, there is no reason for them to jump and all of a sudden gain a momentum just because of going through this small hole, okay? So now there is a problem in here because technically the momentum should stay in the x direction, but for some reason they gain a little bit of momentum in the y direction. So this is the x component, which is roughly equals to p. And this is the momentum in the y direction, which is really the change in p, because as a vector, this is how this looks like, the new momentum. So p prime looks like, from this picture, as just the sum of p plus the error, if you wish, or the change in p. Okay, so this is the change in p. Okay, and in this notation, that's how it looks like. Basically, from this picture, actually, it looks like, since I'm looking at the particle in here, that the theta itself is governed by this expression too, namely that theta 1 from this expression, tangent of theta, is equal to, actually not approximately, is equal to the value that I'm measuring for delta p divided by this p, okay? However, you have to understand that I could potentially, this is the first fringe, okay? The second one, delta p, is actually higher. So the change in delta p is at least for theta 1, okay? So delta p must be at least equal to, if not greater than, so this is theta 1, theta, by the way, or look, still small approximations. So for theta, at least it's equal to theta 1, because that's where I will find the first one, but potentially it can go higher and higher, and I find more and more. So basically what this expression is saying then is that the change in p is p times theta, okay? So that is the minimum, p theta 1, okay? And theta 1 is given by this expression as being simply equal to, so delta p, the change in momentum in here, if you wish, and the error in the measurements of the momentum. That's how we're going to assume in this case, because there is an indetermination. Even in this situation, when I'm saying that the photon is moving in the x-axis, if I go and zero in on it and make this a as small as possible to find how much momentum in there, I mean, to find the position of that photon, there is an uncertainty in this case on the momentum, because this expression actually tells me that too. Yeah, from the diffraction in here. Let me go back into the first experiment, the one that talked about it. This expression clearly states that basically in this case sine of theta is equal to m lambda over a. If I make a smaller, theta will become bigger and bigger. So that's basically, there is a spread in this case, okay? So there is a limit on a, on how we make it. So if we want to fix at least the position of the particle, we're gonna end up with an error in it. If we're gonna fix it in the y direction, its momentum in the y direction, delta p basically in the y direction, will become completely unknown. That is basically what the principle, or the Heisenberg principle is going to be. So in this case, I'm going to plug in the expression for a. I mean, for theta 1, it's just lambda over a. So basically, p times lambda over a. And I was arguing in here, a itself is going to be what is known as the uncertainty in actually in the y-x direction. So if I want to make a equal to 0, then I have a problem in this case. So this is basically, I'm trying to localize or pinpoint this photon. So squeeze on it as much as possible so that I know exactly what it is. But if I do that, that's what the A becomes then. Then I don't know what its momentum is, because this relationship, so I'm going to call this one delta y, if you call it delta y, and that is the change in the momentum in the y direction, if you wish, that is the uncertainty that is coming from it, is greater than or equal to p times lambda. Remember, I just argued that p as itself is equal to h over lambda, so p times lambda is actually h. So this argument in here says that the uncertainty in position, I'm going to write it delta x in general, that's how we write this expression, times the uncertainty in the momentum is greater than or at least equal to h. Okay, this is actually not a complete picture, because we just took a photon and we started discussing this thing about it. In real mechanics, we use actually a statistical, in quantum mechanics, we use statistical analysis and argue actually it's greater. The limit is not actually h, but it's less than that. Actually, it's h bar, which is h over 2 pi. Okay, so that is basically the uncertainty principle of Heisenberg. That basically states that the uncertainty in the position and the momentum are greater than or equal to this h over 2 pi. From now on, if you see me use the not sure, I don't remember exactly honestly about the h bar, yes, okay, h bar, okay, so the h bar, which is just by definition, if you wish, h over 2 pi, and that is roughly 10 to the negative 34, because 2 pi is about 6.26 and the other one is 6.6, so it's roughly, it's 1 point something, okay, again, joule second. Okay, this is in a nutshell your chapter in here. In the next recording, I will have some problems in this chapter that we're going to discuss. And if you guys have any question, please let me know. Okay, these are the main points from this chapter. Thank you.